Hey, Wheaton North, Mr. Yergler here. Sorry about my clunky little headset. I got to do this so that you can hear me, so just ignore it. All right, let's talk about molecular shapes. Electrons repel each other, right? And we know from Lewis dot structures that there's often a lot of electrons that are present in a molecule. So if there are two bonding pairs of electrons, what's the furthest that they can get away from each other? They arrange themselves in a way that they are furthest away from each other, because remember, these electrons are repelling these electrons, right? And so they form this linear structure where one set of electrons is over here and another set of electrons is over here. So let's actually do a drawing of this in an example. BH2 is a great example of this. There's two bonding domains and there's no unbonded electron domains, right? Both of our electrons are bonded, both of our sites, so to speak, because beryllium only has two bonding sites, right? So those two atoms are gonna arrange themselves in a linear structure because that's as far away from each other as they can get, okay? So we would call this structure linear. So we would write linear. So go ahead and write these along with me. Now, what if there's a third bonding domain? Each balloon represents an electron pair, or a bonding pair, from one bonding domain. If we only have three bonding domains, those electrons are going to push away from each other and get as far away from each other as possible. They're going to spread out as much as possible. So these are going to form what we would call trigonal planar structure. Trigonal meaning there's three of them, and planar meaning that they are all in one plane, right? No matter how I rotate this, my hand is a little in the way, so it's kind of hard to bend my arm in a certain way. But no matter how I rotate this, they're in one plane, right? There's nothing up here and there's nothing down here. They're getting away from each other as much as possible, as far as possible. Like this, trigonal planar. It's kind of hard to see with the glare. Now, normally, your Lewis dot structure would look like this, where you have the F's arranged kind of at 90-degree angles, right? But what we're saying here is that this is not completely accurate. These electron pairs are going to push away from each other as much as they can, and so they're going to spread out into this trigonal planar arrangement, which is actually 180 degrees, or I'm sorry, 120 degrees rather than 90 degrees. Okay, so just remember that these Lewis dot structures are great for showing us what the shape will be, but they don't show us the actual shape. Okay, let's look at the next one. 4 bonding domains. Ready? And here it is. Notice that we're no longer in one single plane. These balloons, the blue, green, and yellow balloons, are somewhat pushed down from the orange balloon, right? The orange balloon is kind of pushing up on them as much as possible. And so they're still arranging themselves in a three-dimensional structure. My hand is kind of getting in the way, so you don't see the structure perfectly. But they're arranged in what we call a tetrahedral structure. 4 bonding domains, and they're pushing away from each other as much as possible in 3 dimensions, not in 2 dimensions. So we have to kind of, the balloons kind of help visualize this, because you can see, let me turn them a certain way. See, the orange is not perfectly in line with the other ones. They're kind of angled down a little bit. Okay, let me draw a structure for this. Here it is. It's called tetrahedral. Okay. Again, the Lewis dot structure shows that there are 90-degree angles between all of the different bonds. But the balloons tell us that in reality, these are spread out in 3 dimensions. So the H might be below, and these other 3 H's might be hovering kind of over here in not quite a 90-degree angle, because they have 3 dimensions that they can spread out, not just 2. Okay, so remember that these are not 90 degrees. They're actually 109.5 degrees, but we're not going to have you be concerned with the actual angle. Okay. Now, this is really all the different options that we have, right? 1, 2, and 3 bonding sites, and they're all filled. But what if one of those bonding sites isn't filled? Let's take a look at tetrahedral, but let's remove one of those bonding sites. Okay, so here we have our tetrahedral structure again. But like I said before, we're going to remove one of these electron bonds. Now, the electrons are still going to be there. So here we have an example of a case where we have still 4 bonding sites, but only 3 of them are occupied, right? We have one lone pair. So we still have our tetrahedral shape as before, right? Because we still have 4 bonding domains that are all repelling each other. So it's tetrahedral structure, but it's not a tetrahedral shape like it was right here. The reason is because one of those isn't bonding, right? So there's no other atom up here. So let's get rid of one of the balloons to kind of show that. Let's get rid of the blue one. How about that? Okay, so now we've gotten rid of the blue one. My hand is kind of helping to kind of act as if the blue one was still there, because in reality those electrons are there. They're pushing down on the ones that still are bonding. Okay, so we have what we call trigonal pyramidal shape. It's a tetrahedral structure, but the shape is trigonal pyramidal because we have that one lone pair that's kind of pushing down on the other bonds, right? Remember that all the electrons are still trying to repel each other. And so these are not in the same plane, even though they might look like it a little bit because the balloons aren't a perfect representation of it. But we have this lone pair of electrons repelling those bonds, and so it kind of pushes them down into this like tripod kind of shape, right? A trigonal pyramidal is what we call it. Now, what if there's only two of those domains that are bonded and two of them that are unbonded or lone pairs? Okay, let's do an example of that. Water is the most common example of what we call bent shape. We still have a tetrahedral structure because we have 4 bonding domains, but only 2 of them are actually bonded. So here we have our tetrahedral structure again. And let's get rid of 2 of them because we only have 2 bonds. 2 of them are lone pairs. So let's get rid of 2 of them. Now, remember, those electrons are still there. There's just no other atom present that we can really show with like a balloon, for example. Okay? So let's say that there's still two electrons, maybe like 1 pair here and 1 pair here, pushing down, repelling these other electrons that are involved in these bonds between the oxygen and the hydrogen. If you think of the very point at which the balloons are meeting, where I'm holding them as the oxygen atom, and the end of the balloons being the hydrogen atoms, right, and then the electrons in between that are being shared, we have a bent shape because of those other electrons that are pushing down, repelling these electrons. Let me take a step back and you can have a good look at this board. Make sure you get anything down that you might be missing. You should be able to, from any Lewis dot structure, identify the shape. It will be one of these 5 shapes. So it might be a good idea to practice. Maybe take a random compound and draw its Lewis dot structure. Go back to other worksheets where we've had tons of Lewis dot structures. Go back and assign those shapes to them so that you can kind of get some practice with identifying the shape. It all depends on how many bonding domains you have and how many unbonded domains you have, or lone pairs. As always, make sure you bring any questions to class with you tomorrow. This is Mr. Yergler signing out.